Hello, hello. Ah, I'm on. I figured we'd better start on time, well, if only, because I'm standing in between you and beer. So I appreciate very much you sticking around. It's the last talk of the day, so hopefully it'll be entertaining and informative, which is my goal. So I'm a firm believer. Was anyone in the room here for Troy Hunt's talk this morning? So Troy did a great job, or always does a great job, of telling stories. I'm a firm believer that stories are really important to us in our industry, and in fact that we don't tell enough. In fact, a former colleague of mine, a guy called Simon Stewart, he's now at Facebook, I think, but he's the guy behind WebDriver, if you've ever used that. He has this concept of a team shaman. Right, so this is someone on your team who can tell you the story of how things got the way they are. So I'm going to show my age a little, but I'm joining a new team, and I take a look at the Ant build file. I'm like, oh my God, Taryn, what little hair I have left out. How could you possibly allow this build file to get into this state? And the team shaman gathers the team around and says, I'll tell you the story of the build. Right. It's the idea of the team shaman. I think it's a really powerful concept. Stories are powerful. So this talk really is a series of stories, but the main story is about replacing a $3 billion a year science publishing platform. This was a program of work I was involved with in starting in the UK a couple of years ago now. The idea being that over time, the existing science publishing platform, this is the thing that if you're a researcher, you would submit a paper to, or if you're a researcher, you look for relevant papers on. And over time, this thing was 15 years old, the existing one. And it was an old C++ application, service-oriented architecture, actually, which had done a great job. If I write software that lasts 15 years, making $3 billion a year, I'm going to be quite happy. But it had become quite slow to change, difficult to change. After 15 years, concrete had been poured on it, essentially. And also, business models had changed, and the environment, the world had changed. So they asked ThoughtWorks in to help them out. So that's what the main story in this is about. I talk about software architecture in the title. So the first thing I'd like to do is give you a definition of what I mean when I say software architecture. And specifically, software architecture as code. So I'm going to reach for Martin Fowler's definition here. So Martin says that this software architecture is the stuff that's hard to change. It might have been said earlier by Ralph Johnson. Martin can't quite remember. But the decisions that you make that are hard to change. So explore a bit about what that might mean, what those things are. Maybe programming languages are traditionally hard to change, especially if you're building monolithic applications, domain application protocols, how we coordinate different parts of our software estate, systems estate, communicating. The process boundaries that we're running on, or within. Which integration protocol we're using. Are we using a RESTful style? Are we using RPC? What hardware environment are we going to run it in, and how is that going to look overall, the deployment topology? All of these are traditionally quite hard to change. This talk is about answering this question, really. What happens if these properties, these characteristics, constraints that we work within as architects, developers, what happens if these become easy to change? Because I think they have. I think calling out a few here, if you're building a microservice style of system, then you can choose appropriate programming languages. I'm not suggesting that suddenly everyone goes off and chooses a different language for every service that they're building. That would be anarchy, chaos, although there are some organizations that choose that. But even in big organizations, it makes sense to say, this thing over here looks a bit data science-y, let's use a data science-y thing to solve the problem, as opposed to Java everywhere. Maybe we could use R. Process boundaries are morphable now. If we're designing systems around sort of business concerns, business capabilities, all right, whether that's in a monolith or in a microservice architecture, we should be able to move these components around. Modular applications, modular system architectures allow us to morph and split and join across processes. And recently, with the advent of cloud native, and this is, thinking about it, it's only the last 8 or so years people have been in this space, our hardware environments and deployment topologies have also become easy to change, right, through writing code, infrastructure as code. And this is kind of interesting, because for me, I've got this feeling, I'm sort of running to catch up with the implications of all this. This idea that things that are hard are now easy. Now, I'll give you an example. I was working at a telco some years ago, and we were building a pricing engine for them. We needed, our production environment was going to look a bit like a sort of clustered Oracle database. We were going to have, kind of highly available load balancing, etc. So we sort of submitted a ticket for our requirements for a developer environment with this sort of hardware. And we got a great, yes, approved, and it'll be with you in 9 months. Those days are going. Those days are kind of disappearing now. I'll give you another example of, I think, how it's taken us some time to catch up with the possibilities that are out there. What does disaster recovery mean in the world of cloud native? If we're designing applications to be cloud native, sort of reliable, using chaos engineering, designing in operability characteristics, what does disaster recovery even mean? Gone are the days of saying we need to run active, passive across 2 data centers. Right? We run active everywhere now. My favorite example of this is Netflix. I don't know what percentage it is. Last year, they were about 30% of the world's internet traffic, right? It's a lot. And disaster recovery for them has a vastly different meaning than it has done in the past. It means running always on, all the time, everywhere. Adrian Cockcroft tells the story of how they use, he's the former VP engineering there, how they use Europe for UAT. Right? How do you performance test? How do you create a performance test environment for something that's running 30% of the world's internet traffic? So I think we're sort of playing catch up a little bit with the things we can do with this in this new world, cloud native, infrastructure as code, microservice style architectures. So the story's about us trying to do something a bit different, making decisions in a slightly different way. But first I'll ask this question: how do we normally make decisions about designing software architecture? Well, we do it based on experience. I'm very lucky. I've worked for ThoughtWorks for 13 years, which means I've worked across so many different domains, lots of different verticals, lots of different technologies. I've accrued a lot of experience. So yeah, I can make decisions based on that experience. That's good. But with experience comes another thing as well. Various sets of biases creep in, right? Things like survivorship bias. Just because it worked last time doesn't mean it's going to work the next time. So experience is good. We've got a lot of experience in the room, I can see. But there is a tendency for us to want to make the same decision twice. We also do it based on gut feeling. And this is a good thing as well. Oh, this feels like the right solution. Feels like the right thing to do. And actually, gut feeling is a good thing. Insightful-based decision-making is a sign of expertise. I won't talk too much about it, but there is a thing called the Dreyfus model of skill acquisition. And that describes how we acquire skills over time. And the interesting thing is, as we become an expert in a thing, our decision-making changes to be insight-driven. We no longer maybe can explain why we made a decision. So gut feel is good. But C point 1, survivorship bias. We still often make decisions up front as well. Think really long and hard about how to solve a problem. And personally, and I sort of first heard this argument from, I think it was Dan North. Personally, I think that's because we adopted the wrong model as engineers. As software engineers, we said, we'll copy some stuff from civil engineering or the other types of engineering, where upfront design makes a lot of sense, right? So, civil engineering, I want to build a bridge. The things I'm going to do are I'm going to design the bridge. I'm going to get an architect. They're going to design the bridge. That design is going to be mathematically tested and verified, essentially, using a whole bunch of equations that we've developed over the years. And then we're going to farm it off to subcontractors to just build the thing. And the interesting thing about bridge building, or hospital building, is that it's what's called a reducible problem. you can break it up to its constituent parts, stick it on a Gantt chart. This is what Gantt charts are for. The problem with building software, writing software, is it's what's called an irreducible problem. You can't necessarily break everything up into small parts, stick them all together on a Gantt chart, and do it again and expect the same outcome. And that's because building software is an example of what's called a complex adaptive system. So complex adaptive systems were, I guess the name comes from the Santa Fe Institute. It's a cross-disciplinary institute constituting physicists, mathematicians, biologists, chemists, created by Murray Gell-Mann, to look at the class of problem where if you put essentially an input into it, it's so complicated internally that if you do it twice, you won't necessarily get the same outcome at the end. And software is like that. Building software is like that. Actually, the team building software is like that. It's a complex adaptive system. The organization the team sits in is a complex adaptive system. And this should be obvious if you think about it. So, we pair program at ThoughtWorks. We're a sort of extreme programming shop. So if I'm sitting there with my pair one day, and there's a user story it's going to take 2 days to implement, and we're happily pairing away, and suddenly, overnight I fall sick, and I can't turn up the next day. All right? The code I would have written, the design decisions I would have helped to take, the direction the software would have taken, is going to change. You can never run the same project twice and get the same outcome. So this is interesting. This upfront decision-making, which we've adopted, maybe doesn't actually apply with what we do. So I'm going to try and answer this question. Can we make decisions more systematically, more cheaply, and what would that look like? I'll skip over this briefly, but I work for ThoughtWorks. We do a whole bunch of stuff. I got to go on a sleepover at Martin Fowler's house to write this article on microservices. I'm only going to be talking tangentially about microservices. So I promised you a story, and I'm going to tell you a story. It's a very particular type of story. In fact, it's a restful story. It's a restful book we're going to read together. And that should become obvious in a moment. It's a very particular type of book. This is its name. The Endlessly Bifurcating Trousers of Reality, hat tip Terry Pratchett. And the reason it's a very interesting type of book is it's what's called a choose-your-own-adventure novel. Now, who's come across or read a choose-your-own-adventure novel? I'm dating people here, so I apologize for you having to put your hand up. For those of you who haven't come across this, the idea behind Choose Your Own Adventure, the Warlock of Firetop Mountain, the Forest of Doom, these kinds of things, which were very popular when I was a lad, there is a quest that a mighty hero or heroine has to go on to solve a particular problem, slay the dragon, kill the warlock. This Choose Your Own Adventure, the quest was to build a publishing system. Let's see how it starts. The lawful good product owners of the publishing house had long lived in awe and fear of their publishing systems. In awe, for they had made a tremendous amount of gold, but in fear of the time taken to change them, their slowness and their fragility. A messenger was sent to fetch help from a distant land famed for its mighty wizards. You have taken up the challenge. Now, I mentioned at the start, this was a 15-year-old service-oriented architecture that was already in place. ThoughtWorks were engaged to replace this system. And the reasons were because it was unmaintainable, but also because the world had changed around the system. It turns out China's a thing, right? 15 years ago, China wasn't quite the research behemoth it is now, but actually now the vast, I don't know if it's the majority, but certainly a tremendous amount of global scientific research publishing is coming out of China. And page load times for this thing in China were about 15, 20 seconds, something like that. I'm going to be careful with this now, because it was the same in Australia, but that was probably, you got the internet in about, what was it, 3 years ago, something like that? You still get the AOL discs through up until that point, right? I was told, I don't know. But 15 seconds is not a good look, if you like. And also, it kept crashing. It was very unstable. Let's see what happens next. You must save the product owners by rebuilding their website. You start off the project. In the course of discussions, you discover that your goals are threefold. Improve availability, performance, and maintainability. An enterprise architect approaches and addresses you. You may use summon walk-in skeleton, turn to page 4. Or you may cast analysis paralysis, turn to 3. If you have none of these things, you will have to draw your sword and fight. Analysis paralysis, this is the thing where, oh, I'm feeling a bit tired. I need 6 months to sit in a room and write requirements, right? This is analysis paralysis. A walk-in skeleton, on the other hand, is a sort of more modern, I'm sure people don't know this, but a more modern approach to starting off a software project. This is where we build a thin slice vertically through our system and have the ability to push that through into a production-like environment, as opposed to building all the services and the database and the UI separately, right, and slamming it all together at the end. So what should we do? Choose your own adventure. I should point out this is the gateway drug to Dungeons and Dragons, by the way. So I also play that. What should we do? God, it's like the end of the day. Don't ask me to make decisions. Someone's saying turn to page 4, summon walking skeleton. I might draw my sword now. Actually, what we did, I was a bit tired. I'd just come off another project. We cast analysis paralysis. You cast analysis paralysis at the enterprise architect. Foolish young adventurer, says the architect. We follow the evolutionary ways, and we shall have none of the lawful evil ways of waterfall. The last thing you see before everything goes dark is the architect incanting in a strange voice. You have died. Turn to page 1. That didn't work out very well. They were a fairly forward-looking organization. They wanted to adopt as many sort of better practices, ways of working as they could. So instead, we summoned a walk-in skeleton. Your walk-in skeleton coalesces in a cloud of noxious gases and solidifies as a Java drop wizard application. You reach into your backpack and deploy the content store. Your walk-in skeleton reaches out its skeletal arms and grabs armfuls of raw XML. Would you like to transform the XML inside the skeleton or use a magic box? So fundamentally with publishing, the problems that you have are how to turn a crap load, and that's the technical term, of XML into something human readable, right? And that's, for the kids out there, that's not JSON. JSON is not human readable. It's HTML that we can serve up to a browser. That's pretty much the complexity. There's all sorts of stuff around how you render mathematical formula and graphs and all this kind of stuff. But fundamentally, that's the problem. The difficulty comes around the outside of this. Things like authorization, identity, and things like that. So we've built our little walk-in skeleton. We've got our content stored in S3. What should we do next? And fundamentally, we've got these two different decisions we've got to make, right? We've got a decision to make. We can either transform the XML by writing a library, say, in process, in the walk-in skeleton, or we can create a microservice and do it externally. Let's see what we did in a moment. Because this is really fundamentally how I think about software architecture now, especially about evolutionary architecture. It's about these branching decisions that we have to make as a team, as an individual, when we're working in software. To see what I mean, on the one hand, we've got the idea of creating a microservice to transform this. On the other hand, we can do it in process. Right? Two different decisions. And in this great sort of solution graph, if you like, solution space of all the things, all the ways that we could end up designing and building and delivering this piece of software, we've come to a fork in the road. Our trousers have bifurcated, if you like. Because on the one hand, reductio ad absurdum, we've got a distributed system, and on the other hand, we've got a monolithic MVC app. So these little decisions drive bigger decisions and have consequences later on. And so I would assert that we have a way now of deciding which path to follow in a more effective way than we had before. I said betting on software architecture as code in the title very explicitly. And the reason is I really like this idea of betting. Betting, the act of gambling money on the outcome of a race, game, or other unpredictable event. And there's two things I'll call out in here. The first is this outcome. Did the horse win or lose? In our case, was the decision successful or not? Right? At which point in time? An unpredictable event. I already mentioned this idea of complex adaptive systems, that we're in one, we are one, we're building one. There's all sorts of unpredictability going on. So betting seems like an appropriate idea. And I assert that evolutionary architecture, it allows us to place much, much smaller bets, right? We can place much, much smaller bets. We can keep our options open. We don't have to decide everything up front. Whereas if you're following sort of upfront design, thinking really long and hard about stuff at the start of a project, what we're really doing is closing down all those options. We're saying we know exactly the right path to take. We're going to bet the house on black, bet all our money on black, say. Now, fine, James, that's great, optionality, we want to place small bets. But, surely in high-risk situations, we should be doing something different, right? We should be thinking really long and hard about stuff. I'll give you a few examples of some really high-risk, high-impact programs from history. So back to 1961. And the funny thing happened in 1961, which is President Kennedy said, everyone knows this, I'm sure, by the end of the decade, we will have a man on the moon. Something like that. So here's my question. What did NASA's Gantt chart look like for the Apollo program? I sort of tried to put one together. It looks a bit like this. We're going to spend a load of time thinking about designing the rocket, right? Because we're smart, we're NASA, right? We're literally rocket scientists. We're going to spend a lot of time thinking about it. Then we're going to build it. Then we're going to launch it. We're going to zoom through space. And then we're going to land and then come back and have some tea and biscuits. Now, who in the room, and I've asked this question several times over the course of the last sort of 6 months, who in the room thinks it looks like that? Yeah, I bet there is someone, but you're not sticking your hand up. That's right, because the idea actually that, faced with this task, this monumental task, never been done before, that President Kennedy would make a speech, and then there would be this linear path all the way through to tea and biscuits, right? Using my directed evolutionary graph again. This is kind of a nonsense. In fact, what they did is created options, right? They applied the same sort of thinking that I've been talking about with software architecture. They said, we've got a ton of questions we can't answer. How can we answer these questions in as low a risk a way as we possibly can? So they designed a series of experiments to answer these questions. Can humans survive in space for long enough to get to the moon and back? Can we dock a spacecraft with another spacecraft? Can we even get to the moon? Can we take what we know about orbital mechanics, write some software, and stick it in a computer, and be able to get a rocket to the moon and back, or to the moon even? Is it going to be cheese when we get there? We don't know, right? We've never been before. Is it even safe to land on the cheese? How do we get the returning spacecraft home? Now, this is incredible to think that at that point in human history, we couldn't answer these questions. And so what they did is design a series of experiments to answer them. This is the first one, and this is true. Can we even get to the moon? The range of missions, 1961 to 1965. And this was designed to answer this question by literally throwing a dart at the moon and seeing if the dart hit the moon. That was the experiment. They ran it multiple times. The first one, there was a launch failure, Ranger 1. The second one, there was a launch failure. The third one got off the launch pad but flew straight past the moon, missed it completely. Next one, hit the moon. Unfortunately, they didn't get any data back, so still a failure. The next one, flew past the moon again, missed it. The next one, it impacted on the moon, but the cameras had failed, so again, they didn't get the right data back. At this point, they must be thinking, oh my actual God, we've only got, sort of 6 years left or whatever it is before we've got to get people there. Are we ever going to see any success? Well, the next one actually worked. The next one was a success, impacted on the moon. The next one impacted on the moon, and the next one impacted on the moon. And I should point out, these are a series of experiments, hundreds of millions of dollars per launch. Right. None of these were failures, if you like. Right. They were successes because they learned more about how they were going to answer this question. And this brings an important point in about sunk costs in our organizations. Often we don't see failure as an opportunity for learning. Fundamentally, this is what this was for them. It was an opportunity to learn. The next one, in parallel, was the Gemini mission. So this was to answer the questions, how long can we survive in space? To answer the question, can we dock one spacecraft with another? And how do we get the returning ones home? In parallel again, Surveyor. So this is to try and find some landing spots and to work out whether it's safe to land on the lunar surface. Massively expensive, but the lowest risk way they could go about doing this. There are no people involved in trying to hit the moon or seeing if they could find a safe landing spot. The people were kept in Earth orbit. So that's how NASA solved the problem, massive parallel experimentation to try and reduce the risk. They had some failures. This is my favorite. This is something called the Rogallo wing, and it was one attempt to answer the question, how do we get humans home from space? The Rogallo wing was literally a big hang glider that popped out the back, so the command module floated down. And this, I think, was an evolutionary dead end. I like to think that there was a project manager somewhere who just was new to the project, and the team shaman gathered them all around, and he said, no, we're not doing this, right? And in the end, of course, they did discover an appropriate mechanism, which was parachutes in the sea. Elon Musk, of course, is following the same sort of idea at the moment with SpaceX, right? Except he's landing these things. But of course, they kept blowing up. Elon Musk has famously sort of said, these aren't failures, right? We've learned something. The next time it'll be a success. And now all the rockets that go up are pretty much all reusable. So we can pretty much say that the Gantt chart didn't look like this. Bit further back, 1945, the making of the atomic bomb. Now this is a wonderful book. It's the history of nuclear physics from about 1860 or something like that to about 1945. Now, obviously it's a horrifying period in human history, and this book does not shy away. I will freely admit that the last two chapters had, well, there was, let's just say someone was cutting an onion nearby, shall we? But it does describe this incredible concentration of human minds. At one point in Los Alamos, they would run a poker night on a Friday night. And at that poker night, they would have 13 then current Nobel Prize winners playing poker. And that didn't include the ones who went on, Murray Gell-Mann, Dick Fireman amongst them, to win Nobel Prizes afterwards. It's probably the greatest concentration in human history, apart maybe from Google now. Right? I mean, Google's in the same sort of level. And in this, there's a great quote, because how they solved the problem, various types of problem, were again the same, they used the same approaches. They were unanswerable questions at the time. And yes, they did a lot of thinking, but they had to run experiments. Often with very imprecise information, imperfect information. So the guy who was in charge of this from the military's perspective, this is description, he had to begin building before he knew precisely what to build. He worked from the general to the particular, from outline to detail. An example would be, how do we get enough enriched uranium to build the bomb? There were 3 different approaches. They didn't know which would work, so they did all 3. And Niels Bohr famously said about this, do you remember that I said you wouldn't be able to do this without turning America into a factory? Well, you've turned the US into a factory. But the point was, the only way they could make progress in unknown circumstances, answering these unknowns, was to experiment. Coming forward in time a little bit, back towards us, how to land on Mars. So this is the Curiosity rover. This is how the Curiosity rover landed. And there was a great keynote I saw from the principal investigator, Anita Sengupta, for the landing bit. And she described how they worked out how to land this rover. And none of it involved sending a rover to Mars. It was all about experimentation here on Earth, using simulations, using modeling tools, making scale models. Right. Parallel experiments running along with all the other groups. Because the question is, how do you test how to land on Mars, really? Because without going there, it's very, very hard to test landing on Mars. I was at this keynote, and at the end of it, she took some questions. And of course, being engineers in the room, someone put up their hand and said, yeah, this is all very well, simulations and more, but what about redundancy? What about high availability? And she sort of doubled over laughing at this idea. Because the concept that you would build redundancy into your system when every gram of weight on this thing massively increases the amount of cost, right? Massively increases the amount of money you need to spend on, the amount of fuel you need to use to get out of Earth orbit. The idea of redundancy is ridiculous. So they did modeling, this simulation. Same actually in Los Alamos, Monte Carlo, the modeling tool, the Monte Carlo tool, technique rather, came from Los Alamos. So what do all these things sort of have in common? Well, they're definitely high risk and high impact. Right? If you think about failure of the Apollo program, that's people dying. Manhattan Project, this is losing a war. And Curiosity, it's billions of dollars of investment. And they're also hard to reason about without following a scientific approach. So these techniques that they used science. They rubbed science on it, right? They used things like concurrent set-based engineering. They ran simulations. They did rapid experimentation, and they used modeling techniques. So it turns out all of these things are examples of creating options. They essentially bought options by running these experiments, forming hypotheses. And it's about placing bets, this betting idea, for only the money that they can afford to lose, or the people, the lives. This is not just about money. And so this is demonstrably good for risk reduction, high impact, high risk situations. But it's actually better than that, because in the real world, in financial markets world rather, options have value. Does anyone know what this is? Hand up, any bankers in the room? Investment bankers in the room? No. So this is the Black-Scholes equation. So this is the equation that gives you the price, the value of an option, as in the financial instrument, an option. The interesting thing about this equation is it has this term, sigma, in it. And the sigma term is the volatility of the underlying instruments. This is why traders like volatility, right? Because you can use these instruments to make money in a volatile market. So, if you're in Bitcoin, if you're trading Bitcoin derivatives, that's probably a good idea. Bitcoin options is probably a good idea, although I'm not qualified to give any investment advice, so I should point that out. So this sort of got me thinking. This is a slide from the ThoughtWorks technology radar, showing the themes over the last 10 years. Interestingly, things like containers only sort of turn up 3 or 4 years ago, 5 years ago. I mean, obviously the base tech for it has been around a long time. Every 6 months, I go to the ThoughtWorks face-to-face where we put the tech radar together. We have over 300 new items of technology to consider. Every 6 months. Churn in our world in the world that we live in as technologists is massive, and it's increasing. But also, business models are changing. Banks are up against challenger banks. You can't go to a meetup in London without a fintech CTO giving you a MasterCard instead of a business card. InsurTech is the thing. We're in this world of churn. And the interesting thing with that is, in a volatile market, options have more value. So actually keeping these options, having the ability to create these options, the ability to change direction quickly, that's more valuable, economically more valuable, the faster things are changing around us. So to summarize this a little bit, so by creating options, we not only reduce risk, but we can take advantage of the fact that things are volatile. We can move faster than our competitors, fundamentally. Back to the story. You throw the magic box in between the walking skeleton and the content store. A villager approaches and exclaims, "This beautiful content I see before me. It takes an awful long time to get here. You must somehow make the content arrive faster. If you have a HTTP cache in your inventory, you may use it now." And we can either cache in between our content store, S3, and the content service, or between our walking skeleton and the content service. So we had some pretty stringent requirements around performance, which I'll come on to in a minute. The other things we had to do was be highly available. The reason we needed to be highly available is the MVP for a science publishing site is literally a list of links that you can click on and download a PDF. If you can do that, that's pretty much, you can make money. But the key thing is the page has to be there to click the link. Right, so it has to be available because you understand who clicks the link, who they work for, and then you charge that organization for clicking the link. It's so important, in fact, that the CEO of this company reports a proxy for number of links clicked in their quarterly statements. Pretty important. Performance, similarly. We want to be able to have people in China, in Australia, all around the world access this content. Because if they can't, less links are clicked. So we'd hit this point where we'd slow down. Well, when we started performance testing, rather, we realized we weren't hitting the performance requirements that we had. This is the kind of architecture diagrams I draw. If you know Simon Brown, I drive him to absolute distraction with my diagrams. But essentially, we have this computationally expensive service using probably the best functional programming language in the world, XSLT, to turn XML into HTML. We had a bunch of stuff around the side, so citation services, recommendation services, access, authorization, and authentication services, etc. But this is fundamentally the heart of the problem. And we thought we'd just stick a cache in because we had to meet these requirements. 0.8 seconds time for first byte, 1.5 seconds for page load globally. Now, this content, some of these papers are 50 meg, some of them are 200 meg, quite big. And when we first started looking at it, this is the sort of thing we saw. 35 seconds for page load. Now, I'm not a mathematician, but I do know that 35 is more than 1.5. Ooh, excuse me. And again, using this sort of graph idea, we've hit this decision point. Right. We've detected performance problems. What are we going to do? We've got options. And the fun thing was, because we were running in a cloud native, we were on AWS, cloud native, these decisions were really lightweight. Adding a cache, actually, is what? Downloading a few Docker containers, standing up a few instances somewhere, right, for Varnish. A few lines of code, or some lines of code, certainly less than half a day's worth of code. And we can push that through our version control system, and up pops a nice Varnish cache. Pretty lightweight decision, really. Let's explore this a bit more detail. Let's just add a cache. We decided that we'd put this cache in front of our computationally expensive service. I don't know if anyone in the room, has anyone in the room, I'll ask, worked with sort of reverse proxies or object caching and these kinds of things? Got a few hands up. Now, the thing about caching is you really have to understand what the content looks like before you think about caching. If you think about news media, newspapers, most of the access for content of a newspaper is the stuff that's in the headlines or today's news. This is really, really cacheable. Most people are hitting these things, so you're going to save lots and lots of origin fetches by serving something from a cache. You've then got this really long tail. The problem with science publishing, on the other hand, is that you're, to first order approximation, as likely to access something from last week as you are from 30 years ago, essentially. So every single time, you're going to have to go back to the origin to refresh it unless you preload the cache with everything. And we had, well, I said, 200 meg potentially per item of content. And we had 130 odd years worth of journals, plus books, plus individual papers. It's a lot of content. So preloading a cache with that content, So news media, we got this idea of cache hits predominating, but in our case, cache misses were going to predominate. So we'd have to preload the cache. And after all, there are only two hard things. I'm sure everyone in the room knows this joke. Computer science, cache invalidation, and naming things, and off-by-one errors. But I've got a bonus joke for you. For those of you doing any form of message-based integration, there are only two hard things in messaging. Exactly once delivery, 2. 1, delivery order, and 2, exactly once delivery. I wish I could remember who told me that, because I can't attribute it, because I can't remember. My point really is this decision, let's just add a cache, even though it's quite a lightweight decision, is not something you take lightly. Said no one ever. This brings me to the next part of this, sort of in the subtitle, really. A note on hypothesis-driven architecture. Remember I said at the start, this is about things that were hard to change, things like infrastructure, things like deployment, topologies, and so on. Can we use this idea of hypothesis-driven, use the scientific method to make better decisions about these sorts of things? Let's just add a cache. This is my favorite description of the scientific method. This is Richard Feynman, Nobel Prize-winning physicist, bit of a hero of mine. He's got this lovely description where he says, if we're going to try and discover a new law, scientific law, first of all, we guess the thing. We make a guess. And of course, you've got experience. You've got a bunch of experience in the room. Right? We can have insight, gut feel, but we're just guessing about this thing. Then we compute the consequences of the guess, compare the results to nature, and if it disagrees with the experiment with nature, then the guess is wrong. And in that simple statement is the key to science. He also goes on to say, quite nicely, to paraphrase, it doesn't matter who you are, or how great the guess is, or how beautiful the guess is. It's all about whether it agrees with experiment, agrees with the real world. So could we use this idea of the scientific method to make better decisions? What would we need to do? Well, these are the sort of stages, if you like, that he talks about. Observe nature, make a guess, compute the implications, compare with nature, draw a conclusion. What would we need in order to go through this loop rapidly? Well, we need observability. This used to say monitoring, but observability is the thing these days, so I've changed it to observability. Observable systems. We need a brain, the ability to quickly deploy small changes, and lightweight probes to run the experiment. And when I say quickly deploy small changes, I mean the ability to quickly deploy small changes to things that were previously hard. I'm not talking about continuous delivery of features into production. I'm talking about continuous delivery of infrastructure into production. Right, the ability to safely make decisions and push changes to infrastructure into production. So practices that enable these things. So the first is this idea of monitoring, observability. But what do we mean by monitoring? This is a very overloaded term. Is it about the dashboards? Is it about pages? What is it? So I'm going to use Dan North's definition of monitoring. And Dan defines monitoring as 5 things, well, 4 and a bit. So instrumentation, our code and hardware needs to describe what it's doing. Telemetry, we need to get that information to us somehow. Visualization, so we can meaningfully visualize what's going on, the system's behavior. Alerting, the ability to take action on that. And the bonus one is predictive alerting, so the ability to take action in advance of something going wrong. Right? In our case, we were building microservices. This is before service meshes were a thing. So rather than put a bunch of stuff into sidecars, we built service templates that we could rapidly stand up. And in those service templates, we made sure that each service was sort of, had telemetry around a bunch of stuff. So request latency, service health, downstream dependencies, operating system metrics, and request tracing. When I say service health, this is the idea that if my database goes away, I want to be able to tell someone about it rather than just fall over in a heap. I might not be able to do useful work, but I can at least tell someone about it. This was the stack we were using. It's a bit out of date these days, so, but as I say, the program was a couple of years ago now. This was a Java project, so apologies for all you .NET people in the room. This is what our sort of graphite dashboards look like, horrendous. Graphite does look horrendous, but we'd instrumented to the point where we had we knew how long individual XSLT transforms took. That was the level of instrumentation. This is one of our this is a representation of a circuit breaking dashboard. It's not actually ours. I couldn't get a picture of that, but it looked similar. Well, the next thing is continuous delivery. Safely and sustainably reduce lead time to value. These are the 3 monkeys of continuous delivery. So this is Jez covering his face, Jez Humble, one of the co-authors of Continuous Delivery, the book, along with this guy, Dave Farley. He wasn't in the room. But Little known fact, Sam and Dan were also involved early in that project and both dropped out. But all the ideas comes from quite a small group. And when I say continuous delivery, I don't just, as I said, don't just mean continuous delivery of feature code. I mean continuous delivery of infrastructure code, the things that are hard to change. Well, how our environments look, what our firewall rules are, all that sort of stuff, where our environments even sit. This is a build pipeline. I'm sure you've seen many of these before. But this is quite new, this idea of having build pipelines for infrastructure code. Every time we make a change to configuration or to infrastructure code, we push it into version control, and we push it through a build pipeline. This was in the ThoughtWorks Tech Radar a couple of issues ago. Which means we, in theory, can go through this loop now in a really short amount of time, testing things that were previously difficult to change. The next thing is the idea of lightweight performance testing. And I don't mean this whole, the whole stuff, methodology around performance testing. It's a bit of a pet subject of mine. So things like soak testing, ramp up to high load, stress testing, continuous high load, blah, blah, blah. Don't mean that kind of stuff. Instead, what I mean is the idea of sort of simple performance trending. So very early on projects that I'm working on, I like to have simple performance tests running as part of the build. So just a stage off the build, off the critical path, that basically just hammers an endpoint for 60 seconds and then stores that information somewhere. So you can have a look at a trend over time. Am I getting better or worse? And so if you have those sort of tools available to you, you can do cool stuff. And these were the sort of tools we were using. In this project, we tried out Apache Bench, which is, it's been around forever. It's the benchmarking tool for the Apache HTTP server. Couldn't get much easier to run these tools, as you can see. In the end, we decided on a combination of Siege and on Vegeta for various reasons, but Vegeta's nice because it allows you to send requests at a constant rate. So we could use Siege to apply some load, and then use Vegeta to send tracer bullets, if you like, and then measure the latency of the tracer bullets. Separation of concerns between apply and load and measurement. The next thing, as I mentioned, cloud-native infrastructure as code. So my colleague, Keith Morris, wrote this book. It's a great book. And again, we had this in the radar. So the ability to have all your infrastructure code versioned and be able to deploy that by pushing it through a pipeline. And in our case, we were using this stack. So Ansible, Botto, AWS, and Jenkins. Also some other patterns. So we were doing things like canary releases. Right, so we could deploy a new instance of a service, but not direct traffic to it yet, like live traffic to it. And this is a commonly understood pattern these days. So it allowed our QAs to effectively test in production, if you like. We were also using Phoenix environments, or Phoenix everything, in fact, so Phoenix instances, but Phoenix environments. We had the ability to push button, start an entire new production set of production infrastructure, production environment, in a different location. And again, this is going back to this idea of, are we as individuals or organizations understanding the sort of implications of what this sort of stuff allows us to do? If I went to my ops team previously and said, hey, I'd like an entire new production environment, please, how long is that going to take? It's going to take a long time. Well, we need to buy 3 new F5s, et cetera, et cetera. But we have this, all defining code, versioned, and so on. And we were doing blue-green deploys. This is actually an animated GIF of one of our blue-green deploys. So we've got this sort of set of techniques. We've got the ability to sort of monitor, observe our systems. We've got the ability to think, you'd hope. The ability to quickly deploy small changes to the things that were hard to change. And we've got lightweight probes. Let's see if we can put all this together. Otherwise known as science. So if you remember, this is where we were in our story, right? 35 seconds time, for 35 seconds for page load. And these are our requirements. And we'd come up with a number of options. Maybe we should put a cache in. We could cache in front of S3 or cache in front of our microservice. But there are other options out there, much, much lighter weight options. Maybe we could add some more CPUs, see what happened. Now, previously, again, that would be really hard. Hey, Mr. Ops team, Mrs. Ops team, can we just have a new server, please, with more grunt? Yeah, fine, 3 months. But in this case, well, it's how long does it take to change the instance size in an Ansible script? Not too long. So this is what we did. We guessed that by adding more CPUs, we'd improve our performance. We had a look, see what was going on, measured our initial performance, 35 seconds. We made a guess. XSLT can be expensive. Maybe we're CPU bound. We computed the implications, compared the results with nature, and drew our conclusion. And our conclusion was, yes, we were CPU bound, it turns out. So we got down to about 6 seconds by just increasing instance sizes on these nodes that were doing XSLT transforms, which is pretty good, right? The graph that shows that. The next guess we made was maybe we should move compute to where the data live. Now, we'd made a bit of a daft decision at the start, which was we'll run compute out of one of the AWS European regions, but all our data is in S3 in North America. Now, I don't know how good your geography is, but it turns out there's an ocean there. You're losing a couple of hundred milliseconds every time you're going across the Atlantic and back. So maybe we should move compute to the data. So we ran an experiment. We stood up an entire copy of our production infrastructure over in the US. Now, this is a slightly bigger change than changing an instance size, admittedly, right? A bit more code. You need to do things like sort out your keys and all that kind of stuff. But it's not a massive change. It's not a, hey, Mr. CIO, can we build 2 new data centers in the US, please? It's half a day's work. And we got down to about 4 seconds when we did that. The next thing, our transformations are slow. Maybe we should optimize our transformations. As I said, we had telemetry, and we had instrumentation and telemetry around our transformations. So we optimized those, got down to about 3.5 seconds. And the final thing we did, well, maybe we should cache. Bite the bullet. And we decided to put a cache in front of our computationally expensive service. As I mentioned earlier, this was coming with some overhead. We had to preload this cache. And the way we did that was by hooking into the publishing pipeline. And every time a new piece of content was created, we would just use wget to hit the cache, the reverse proxy, which would do an origin fetch and pin that content in the cache. Pretty cool. And at that point, we got down to about 0.2 seconds for page load in the room. A bit more outside, clearly. Woo! Happy times. So again, using this sort of example, using this evolutionary graph idea, we sort of started off going down this path of a distributed system. We created a microservice. We had this point where we detected performance problems, and then we had a number of options that we could purchase and did, and then ran experiments to work out what was the best thing to do next. On the one hand, we've got this cache in front of S3, which is going to save both XSLT transform time, but also the fetch, or we can save the fetch just from S3. Let's see what happens next in the story. Content trickles into the store. You keep up by listening for the new content and casting wget on the cache to keep it refreshed. New types of content appears, content the villagers have never seen before, content the walk-in skeleton is unable to combat. Every time the structure of the content changes, the cache must be refreshed. The cache grows and grows until it's big. It is no longer possible to refresh it. Latency increases. You have died. Turn to page 1. And there was a sort of non-obvious thing that happened, right? We were rapidly developing the API of the content service. Every time we made a change to the structure of the content it was returning, right, we had to blow the whole cache away. And this is a lot of data. So it turned out that our ability to change that service was limited by the amount of time it took us to load the cache. That sucks. We died. Turn to page 1. Do you remember I said earlier that this is sort of a gateway drug to Dungeons and Dragons? I don't know the people in the room who used to read these, but I used to keep my fingers in the book. right? So I could always go back one in case this happened. And Mike Nygaard, the guy behind Release It, when he saw this, he said, keeping your fingers in the book is the gateway drug to version control systems, right? Because it is, in a way. Because we can flip the page back. All this code is versioned. All this code is safely deployable in an automated way. So that's what we did. We reverted that change. It helped that our initial choice of using HTTP, which we did, we chose to do, and using a RESTful integration style, meant that we could take advantage of the uniform interface of HTTP, but we could back out the change of putting the cache in one place and reinsert it somewhere else with a very small amount of change in the code. It turns out that that cache in front of the content service was an evolutionary dead end for us. And in fact, we cached in front of S3, didn't save as much for the processing time, but it still worked. This project's still going on. The product teams building this are still building it. We also built a 200-person engineering team at the same time in London from scratch, and they're charging ahead, delighting researchers around the world with their ability to get customer feedback, client feedback, user feedback, and implement stuff on this new platform. But I think we'll leave the story there. So I guess I'm going to summarize real options and small bets. What do we need to take advantage of this idea of changing things quickly, safely, that are hard to change, or were previously hard to change? The ability to observe nature, the ability to quickly run experiments, and to rapidly change all the things. And this is not new. I'm not pretending this is new. Our colleagues in product, they know all about this. This is A/B testing, right? But I'm talking about applying that sort of same stuff to software architecture. So evolutionary architecture keeps our options open. That has value, right? Reduces risk and has value. It's continuous delivery, lean product engineering, infrastructure as code, reduce the amount of money we need to place a bet. And lightweight experiments allow us to make hypotheses and make guesses and test our hypotheses. I'm going to finish by going right back to the start when I said about how do we make decisions about software architecture. How do we proceed at the start of a project? How do we evolve something? And I said we do it based on experience, gut feel, and by thinking. I'm not suggesting that every time we start a new project, every time we start building a new piece of software, that we start from scratch, exploring every single possible decision that we could make. That would be insane. Or at least very, very slow and expensive. But that's cool, because the experience bit, right, the gut instinct bit, and the literature help us shortcut all of this. Essentially, we don't have to start at the bottom, right at the bottom of this graph here. We start on one of these leaves up the top. Because there's a whole set of work around patterns, there's a whole set of work around pattern languages and books and things which allow us to sort of make these initial decisions pretty quickly. But again, if you think about it, it's the stuff at the top, the stuff that differentiates us, that make us money, right? Or save lives, or do whatever it is that we're doing as the goal of our organization. Yeah. And having the ability to quickly change stuff maybe will allow us to make more money or save more lives. That's me. Thank you very much. I think we've probably got time for one question. Otherwise, I'll be around for a little bit and hang around here. Oh, I thought someone was really disagreeing, was going to come and attack me then. Thank you for staying. I appreciate it's late. All right, we'll call it a night. Thank you very much. Enjoy the boat party if you're going. Otherwise, enjoy the party and the rest of the conference tomorrow.